end-to-end system that uses a Retrieval-Augmented Large Language Model, or RAG-LLM, for cloud-based healthcare. Our main goal is to make the doctor-patient relationship easier and more efficient. The system helps patients understand their condition with the help of AI, while providing doctors with a structured summary and relevant supporting documents. Our research object is the overall cloud-based system. The subject is more specific. We investigate how to use retrieval-augmented generation to boost the performance of language models in medical diagnosis. What's new in our approach is the complete, end-to-end integration of multiple AI technologies. First, we use convolutional neural networks, or CNNs, to process and classify medical images. Then, we add context and explanations using a large language model that's been enhanced with a RAG mechanism. Our vector database includes medical articles and drug descriptions scraped from trusted sources like Mayo Clinic and RxList. All components are hosted in the cloud using Amazon Web Services, making the system scalable, secure, and efficient. Let me briefly explain how retrieval-augmented generation works. Unlike a typical language model that relies only on its training data, RAG systems combine generation with real-time document retrieval. In our case, the model takes the CNN result and patient input, then retrieves relevant documents, such as medical articles or treatment summaries, from a vector database. These documents are embedded as context and fed into the language model, which then generates an explanation grounded in medical facts. This makes the AI more reliable, factual, and less prone to hallucination. This is the high-level architecture of our application. It starts with the user uploading an image of a skin or eye condition. The image is classified by a CNN running in a containerized service. The results are stored in Amazon S3. At the same time, user metadata is stored in DynamoDB. The FastAPI backend triggers a request to our RAG-enhanced LLM, which retrieves relevant content from a vector database, combines it with user input and CNN predictions, and generates a detailed diagnosis or explanation. Doctors can review and edit the output through a secure dashboard, and the final feedback is delivered to the user via WebSockets. Let's walk through a real-world example. A user opens our application, uploads a photo of a skin issue, and optionally describes symptoms. The CNN model analyzes the image and gives a prediction, say, eczema. This prediction is passed to the RAG model, which fetches relevant clinical details about eczema from the vector database and crafts a user-friendly explanation. Before anything is shown to the patient, the doctor reviews it, adds recommendations, and confirms or adjusts the final message. This preserves clinical accuracy while empowering the patient with useful insights. Let's now look at the system from the doctor's perspective. When a doctor logs into the secure dashboard, they are authenticated using AWS Cognito. Immediately, they can see new incoming cases. These consist of a medical image, short patient symptoms, and the AI's proposed response. That response is generated by our hybrid AI pipeline. A CNN provides a preliminary classification, and the retrieval-augmented LLM elaborates on the case, referencing real documents from our vector database. Critically, the doctor is not a passive recipient of this output. They have full editorial control. Within the dashboard, they can inspect the diagnosis, view the classification confidence, examine the retrieved sources, and adjust the final message. This ensures human oversight and protects against false positives or edge cases that AI might misinterpret. Once the doctor finalizes their feedback, it's sent to the patient through the chat interface, ensuring quick turnaround while preserving medical responsibility. According to our testing, this workflow led to a 26% reduction in average case handling time, and physicians rated 89% of AI responses as clinically usable, either as is or with minor edits. In essence, the system doesn't replace the doctor. It accelerates their decision-making by handling routine triage, literature consultation, and initial synthesis, allowing them to focus on final judgments and patient interaction. Here are some screenshots of the system in action. You can see the user interface for uploading an image. After processing, the AI generates a result and a simple explanation. On the doctor's side, we have a dashboard where they can review past and incoming requests, see AI predictions, and approve or revise results. We also implemented a chat window using Supabase to allow users to ask follow-up questions, creating a dynamic, conversational experience. To summarize, this system supports both patients and doctors by offering fast, explainable, and medically grounded assistance. The architecture is scalable and could be extended to more medical areas beyond dermatology and ophthalmology. That concludes our presentation. We hope we've shown not just the technical depth of our work, but also its real potential to support doctors and empower patients. This system is not just a prototype, it's a glimpse into the future of AI-assisted healthcare. One that's explainable, responsible, and designed around real clinical workflows. We're excited to keep building on this foundation, from integrating more modalities like voice and video to eventually piloting the system in collaboration with medical institutions. Thank you all for your time and attention. We'd be happy to take your questions or hear your feedback.